Hi, everybody. Thanks for coming. That was just a montage that we put together of the first few weeks of the summer internship program here at SwarmRobotix. And we've put a lot more cool videos together that we'll reveal over the coming weeks, but a lot of editing yet to do. Welcome to SwarmRobotix. We're a brand new company here in Oswego, and this summer we've spent a lot of time putting together a system that it could have a pretty significant impact on intermodal logistics. And to many of you, that's probably not going to be very interesting, so I hope you'll bear with us while we talk about intermodal logistics. And for those of you that are in intermodal logistics, we hope that you'll bear with us while we talk about something else that's really, really important, and that's education. And so we have two audiences tonight, and we hope you'll bear with us as we talk about container logistics and education. Our ultimate goal is to rapidly develop solutions to fix problems, and we want to utilize our young people to use their talents and give them the resources that they need in order to solve problems themselves, utilizing the technologies that are emerging today. There's a lot of really cool technologies that are emerging today. These guys know it better than most of us that are out here in the audience. They know it better than we do, so I'm pretty excited about what I've learned in the last few months because they know a lot more about technology, automation, LiDARs, Arduinos, Raspberry Pis. They know a lot more about it than I do. So it's been a learning education for me as well. 14 interns came together, and I'm going to talk a little bit about that process, but they've been incredible. This is their 48th day working in the internship program. I wish we had one more day to get ready, but we're going to see how it goes. So everybody says, well, how'd you come up with the idea for SwarmRobotix? And really, if you look out there and you see the changes that are taking place, all the positive things that are happening, a lot of automation, autonomous vehicles, drones, automation in manufacturing, automation in distribution systems, including the Kiva robots. Those are Kiva robots that move the shelves to the pickers instead of the pickers walking around in the shelves. And that's what Amazon's using. IBM's got Watson. They've got artificial intelligence, machine learning, vision recognition. Fiber optic cable is making communications possible. We just had Metronet install fiber optic cable here so that we could live stream this presentation. And it's amazing how much faster the internet is. So it's really, really advancing very quickly, the technology. So about 4 years ago, I went to Neuqua Valley and I saw a competition. It was called Buckyball competition, part of the VEX Robotics program. And they had to move balls from one side of a track to another side, and they competed. There were two robots competing against two other robots on a different team. And I looked at what they were doing. That's my son, the tall one there. And I asked them, I said, where'd you learn all this? And they said, with VEX Robotics in school. It's a school club. And I said, well, are you driving these things? He told me, well, you drive them part of the time, and part of the time they're autonomous. And I said, well, how do you program all that stuff? And he started telling me about programming and the code. And I was like, this is fantastic. We need more of this stuff in schools. We need to see more of this type of work at our K through 12 education system. They won a competition, mostly because of their partners. They have alliances, but they had a really cool robot too. So I said, what if we took these kids that know how to program these robots, and instead of playing games, we start solving real life problems. And so we said, let's figure out what we can tackle. What's the first thing that we can tackle? So I've been involved in logistics most of my life, or supply chain anyway, and I'm very familiar with the man on the left is Malcolm McLean. He invented the box, the sea container, the standard sea container. It has 8 corner castings, 1 in each corner, and goods move around the world in these sea containers. And in the 50s, when he patented the sea container, the cost of moving goods went down, and the ability to transfer or trade went up, because now all of a sudden the cost of logistics or moving goods became much lower. So he invented the corner casting, and he invented the container, and then he also sold his trucking company and bought ships and started putting containers on ships. And back then they had 300 or 400 containers on a ship at a time. I mentioned the corner castings. That's a Maersk corner casting. Maersk bought Sealand, the company that Malcolm McLean founded. But the corner castings are a very important part, because every container can be moved by the corner castings, and only by the corner castings. No other way should it be moved. The container is designed to take the weight only at those points. So what's transpired in the last 40 or 50 years is the ships have gotten bigger and bigger, and his first ships had 300 or 400 TEUs, or 20-foot equivalent units, and those are containers. A 40-foot container counts as 2 TEUs, but a 20-foot equivalent unit is a TEU. So in 1968, the Encounter Bay held 1,500 TEUs. By 2012, the Marco Polo held 16,000 containers, and the ships that they're building right now for 2018 hold 22 or 23,000 containers. And Costco just announced this week an order for 14 more containers ships that hold 22 or 23,000 containers on each. So this is having a big impact on international shipping and also the ports that have to service these big ships. This is one of my favorite ports. It's in Cartagena, Colombia. The ships come into dock, and these are ship-to-shore cranes. These ship-to-shore cranes cost about $12 million a piece, and they move containers from the ships to the shore. And on the shore, the containers get moved to the stacks, and then from the stacks, they get put on trucks or trains that deliver the goods inland. So if we look at this slide, you can see the ship-to-shore cranes, the containers come off the ship, go into the stacks. Typically, they get into a customs clearance process if they're international shipments. Then they get put onto trucks and trains and shipped inland. So the problem that we have is the ship-to-shore cranes require a truck or a chassis or an AGV, which is an automated guided vehicle, to be there when the container comes down from the ship-to-shore crane. And I've seen way too often the ship-to-shore crane, a $12 million piece of equipment, is waiting for a truck or a AGV, and it's losing productivity. In addition, it takes more time to set a container onto a ship, onto a truck or onto an AGV, because it has to precision itself precisely on the pins of the truck. And so this presents a problem, or and I look at it another way, it presents an opportunity to change the way that containers are handled at the ports. This is just one more way that containers are moved. This is a container being loaded onto a chassis of a truck. So let me talk a little bit about swarm intelligence. Swarm intelligence, if you think of a swarm of bees or a swarm of ants, they're very small creatures, they're decentralized, they're aware of their surroundings, they have a system that is self-healing. If you step on one ant, the system keeps working. And it's kind of like our internship team here. We had a couple illnesses, but the team kept working, so I always call them my swarm. But it's a collective behavior of decentralized, self-organized systems, whether they're natural or artificial. So let me tell you about our team. They're going to talk to you about the solution. I kind of talked about the problem. They're going to talk about the solution that we've come up with. But I want to talk about the team first real quick, and then I'll introduce you to a few of our interns who are going to talk about the solution. You don't want to hear me anyway.
Using robots in multi-robotics systems. We're also incorporating high school and college robotics students who have 3 or 4 years of experience building systems and building robots and incorporating the latest and greatest in swarm technology.
My name is Nate Post. I'm team lead of the interns.
My name is Gautam Natal, and I'm the mechanical lead here at SwarmRobotix.
I'm Alex James, and I'm working as a software development intern.
My name is Parth Barat, and I'm a software developer.
I'm Stephanie. I work on the mechanical team.
My name is Daniel Esperance, and I am a research intern.
I'm Rohan Matrilla, and I'm a mechanical engineering intern.
My name is Gopal Maven, and I'm a mechanical intern.
My name is Jason Taximatis, and I'm a software developer.
My name is Max Wang, and I do design and marketing.
My name is Martin Grover. I'm a software developer here.
My name is Rishi Glory, and I'm a mechanical intern.
In 2014, my son was on the robotics team at Mateo Valley High School, and we went to a competition at Equa Valley High School, and I was just so impressed with all of the robots that had been built by these 17 and 18-year-olds. And I thought to myself, wouldn't it be great if they had an opportunity to build robots in the summer after graduating high school and before they started college. And from there, I thought about what are the types of problems that they could work on. And we put together a plan to bring high school and college age students who have experience in robotics to build robots during the summer.
So we did it. We did it beginning in February and March of this year. Nate Post was the first intern that came on board. I was actually at the Oswego Light Show and talked to the robotics team in Oswego. And I mentioned that my idea, and the instructor said, you know, I got a guy that would be great for that. And so Nate came into my office. I hired him on the spot and said, let's do this. He began working with me on the plans. And from there, we built an executive team, an advisory board, hired our interns. But let me introduce you to the team. Dave Lesperance has been a big help. He's owner of Aurora Custom Machine, and he's been helping us with figuring out how to machine parts that are required for our system. Dave Zahn works at Nokia. He's an expert in communication technology, so he's been able to help us figure out how to use all these crazy technologies that aren't even available yet in the marketplace. Some that are, but some that I have never even heard of. Mike Copeland's helped us out a lot. He's a real handy guy and knows how to put things together, very mechanically inclined. Nate, of course, has been our first and lead innovator in terms of putting the parts of the system together. Joe Fairless has helped us out with procurement and purchase orders and making sure that the hundreds of parts that we needed to get got purchased or procured, so he's been a big help there. And our advisory board has been very helpful as well. Gene DeMonte is here. He owns DeMonte Group in Warrenville, and we had to have a lot of parts 3D printed. He has 3D printers, and they were able to help us put some parts together overnight, basically. When we needed parts, he was able to help us 3D print some of the key components. Bill Berlinger is at Caterpillar. He's head of licensing and technology protection, or IP protection at Caterpillar, and he was very influential early on, talking about how important it is to build intellectual capital, or to create ideas, and how to take those ideas from an idea, protect them, and then prototype and commercialize those ideas. So he's a great mentor in terms of figuring out how to do that. He's been a great help in the strategy of Swarm Robotics. Jonathan Whitaker is at Chainalytics, and he's been a real big help in pulling together resources from the industry to understand what our technology is and to give us some peer review feedback on, is it going to work? Is it worthwhile? Should we continue to move forward? And I will tell you the feedback so far has been very positive. Rod McCracken is a very old friend of mine. He's very old, but he's been a friend of mine for a long time. And he's been a lot of help. I worked for him back in the early 2000s when BP and Amical merged. And he was my client at the time. And now I'm kind of his client, which is fun. Gaetan Cherist has been a big help with our animation work. So you're going to see some animation work tonight. That's pretty impressive stuff. He's the man behind it. He's been a great source of ideas and support as we've come through the process of creating an idea and converting it into an animated image. So it's going to be really cool when you see it. I'm excited for you to see it. I mentioned the team members. Bart's been doing a lot of the video footage, actually been our videographer and photographer documenting the process that we've gone through. Dan's been doing research work on patents and also been doing work on grants. So it's been a great help to have him there doing all that deep dive into all the patents and all the work that needs to get done in order for us to protect the IP. And Max has been instrumental in putting together our website, our logos, the audiovisual tonight. He's been behind that along with a couple of the others, but a huge help. Alex is our chief programmer, great software programmer. Jason also is our software programmer, but also behind the controls and electrical systems. Manu's been there working on all of our IT problems and solving problem after problem, keeping us up and running. Nate's been our team lead, and he's the one that's kind of directed the team, although it's been self-governing, much like a Vex Robotics team or a somewhat governing, but Nate's the guy that has to make some of the tough calls. At that. And then Parth has been also real good in our programming. He's a junior at Wabansi, so I'm very excited that he's going to stick around this next year and help me to recruit next year's local high school interns. Our mechanical team was phenomenal. Gautam came up with one of the big ideas that became part of our V3, and we're going to show you some of that information, or show you some of those ideas and designs tonight. Matt's been a guy that would put anything together any way possible. Taught himself, I should say he taught himself how to weld. We gave him some limited instruction on how to weld, and he figured out the rest. And he's done a great job putting things together. Naufal's been our muscle man whenever we need heavy things lifted or moved. He's been able to put things together for us. So he's been instrumental in helping with a lot of the heavy lifting and assembly. And Rishi's been, you'll hear from Rishi in a minute. He's a dynamic speaker. He always has a way with words, and he's really good at helping us to prepare materials for print or for the website, or even for our promotional materials, which will be coming out in the coming weeks. Rohan, brilliant kid, one idea after another that's been very helpful in terms of the design of our systems, and been really good on helping us to solve a lot of the mechanical challenges. And Stephanie is the one who's drilled more holes than anybody in all of this robotic equipment that you're going to see. She's actually the one that's always has the drill in her hand and is putting the holes where they're supposed to be. So I'm going to turn it over, and I said I was going to introduce you to Rishi and Rohan. They're going to come up, and I talked a little bit about the problem that we want to solve, and they're going to tell you what they've done over the last 48 days, 48 work days, 73 calendar days. So I'm going to turn it over to them, and they'll tell you about what they've done.
Testing. 1, 2, 3, testing. Hi guys, I'm Rishi.
I'm Rohan.
And Rohan's going to start by talking a little bit about how the team works together. It's something we like to call structural capital. So different programs and different things we use to really stay organized as a team during the project.
So for communication within our team, we use Discord, which is a chat app, and that allows us to have all of our communications on different channels. So for example, Gautam can be talking to Stephanie about the drive system on the drive channel, and that allows us to optimize not only the way we work, but also our communications. We use Dropbox to store all of our files. For example, this presentation is on Dropbox, and that means that if any computer crashes or something happens, we always have all the files we need wherever we need them. We use Fusion 360 for all of our CAD. Fusion 360 is a cloud-based CAD software, and that means that we can have all of our CAD files on the cloud. And so if Stephanie is working on the drive base on CAD, then Rishi can start working on it as soon as she's done without having to deal with any file transfers. We use Trello for task management so that none of us are ever sitting idly not doing anything, so that we can optimize our time here. We use Zoho for email hosting. All of us have our own company emails at SwarmRobotix.com, and Zoho allows us to do that. And then finally, we use IntelliJ IDEA as our IDE for our development environment for all of our robots and all the code that we have on them.
So while we use a lot of different softwares here at SwarmRobotix, like Rohan explained, we use one the most, and that's Autodesk's Fusion 360. It's a CAD software. Essentially what it let us do and what's so special about Fusion 360 is that, like Rohan said, it's cloud-based. So it's essentially, it's like kind of like Google Drive, where everyone can work on the same document on different computers. That's different to previous CAD softwares. A lot of us have CAD experience, so we know about it, and it really helped us because we were able to transition really well into Autodesk Fusion 360. It was really intuitive and really similar to other CAD softwares. The only difference being that we could all work on the same project at the same time. Rohan can work on a part in the drive, I can work on a part in the lift, and we can come together later when we're done and assemble it. It's different because in previous CAD softwares, we would have to both work on one computer, and essentially it would take twice the amount of time because we're working on 2 times the amount of things. And because of that, Fusion 360 is actually one of the most useful things SwarmRobotix uses.
All right, so now I'm going to speak a little bit about the concept for our solution. As Glenn explained earlier, there was a problem in shipping ports, and that's the optimization of short-range movement. And so what we're planning on doing is using 4 robots in a swarm. So all these robots will communicate with each other and think together to move around these containers. So here we have a top view of the container and how it's going to move. So the 4 robots come to the 4 corners of the container and then pick it up and then move it.
So I'm going to talk about a little bit about version 1, or the proof of concept. Now, SwarmRobotix as a company, we use a prototyping cycle we like to call rapid prototyping. Essentially what it is once we've nailed down a problem that we want to solve, we obviously have to create a solution to that. And in doing so, with the first few weeks in the first prototyping cycle, what we're going to do is what we did was we narrowed down design ideas, figured out something that worked and that we could build a foundation off of, but that didn't necessarily meet the marketable ideal. So it didn't have to be perfect. It had problems, it had kinks, but this is essentially what proved that this is a viable design. And if you look right here, this is what the first design looked like. It's what we like to call V1, version 1, and it's the initial prototype cycle we use. As you can see, you'll actually see it in a bit after the presentation, but it's a very basic system. The main problem with this design is that it had a fixed drivetrain, This means that it can turn when it's outside of the container, but once it's locked into the container, it no longer has turning capability. Now, obviously this is a problem because to be more sufficient in port, you would obviously have to turn with the container. But the reason this wasn't a problem for our V1 is, again, we're just proving viability of the design. We're proving that the design solution that we can have 4 Swarm robots approach a container, lift the container, and then move it is viable. Larger problems in this robot can be addressed in the next design solution, which is what we did, and it's what you'll see in a little bit. Now, the twist lock is what we want to talk about. It's one of the most important parts on the robot, and it's actually how the robot interfaces with the container, along with the corner casting, which is actually at Rohan's speed. Rohan, if you want to point to that right there. That's what a corner casting looks like. Essentially what happens is the twist lock will insert into that corner casting, turn, and then the robot is locked into that container. So because of that, that's actually the industry standard right now, and it's something we wanted to keep standard so that it was as easy to switch from the current AGVs, like Glenn was talking about earlier, into our Swarm robots. There's no need for a long, elongated segue. And this is an animation of how the V1 robot interfaces with the corner casting.
So here you can see that, and imagine that the rest of the container is on the corner casting. The robot lifts the corner with the screw jacks and then drives forward underneath the container and then drops the container back onto the chassis of the robot so that we have better weight distribution for the container on the robot.
Like I said earlier, because it was the version 1 and the V1 of our prototyping cycle, it had a lot of problems. The main thing, like I mentioned earlier, was the turning radius. Because it wasn't able to turn when locked into a container, clearly it's not a marketable design, but again, it's just something we like to use just so we can prove viability. The other 3 main problems were the lifting capacity. The V1 robot was actually only designed to lift an empty container, which is 8,000 pounds, as opposed to a full container, which is roughly 40 tons. Because of that, in later design cycles, we would have to beef up all the subsystems. But again, just in keeping with the idea of rapid prototyping, the V1 isn't meant to carry a full container. The other thing was the lift speed. The lift wasn't fast at all. It takes about 5 minutes to go up and then 5 minutes to come down. Obviously, again, when keeping in terms of efficiency, it's not going to be efficient in a port setting, but it's good enough to prove that the robots can lift the container in the corner casting. And the last thing was that the first version run robots actually had a manual twist lock. So we had to manually engage it with the corner castings. These are just problems that the version 1 had, and because of the nature of the rapid prototyping cycles, it's things that would be addressed in later prototyping cycles.
So this is the solution to all those weaknesses that Rishi just pointed out. So after we built the V1 prototype in our first 5 weeks, we decided that we wanted to build 4 V3 prototypes, or the Swerve modules, for the rest of the internship. So what makes these Swerve modules really unique is that the lift mechanism is separate from the drive mechanism, and the drive mechanism is on a separate bearing. This means that the drive can turn in separate directions, and that allows for us to park containers like parallel parking or do 0-point turns. So now I'm going to hand it off to Jason so that he can explain more of the controls component, the electronics, and some of the low-level code.
Hi, I'm here to talk about low-level code, and before I get into it, I want to talk about what exactly low-level code is when I speak about it. Low-level code is the kind of thing that connects electronic components to a computer. For example, if we put a command into our computer that we want a motor to turn at 1/3 of its full speed, low-level code is what translates that's command into the motor actually turning. So these are some of the components we use in the control. The first one is called a Raspberry Pi. There have been 3 iterations of it. We're using the most recent version. It's just like your home computer, just a lot smaller. It runs a distro of Linux optimized for its processor. Second one is an Arduino Mega. It's called a microcontroller. The idea is it has very simple code on it that runs in serially. It's just one command at a time, and that allows it to output and input electrical signals. The third one is called a SwarmRobotix Spark. It takes in an electrical signal, and it controls an extremely large amount of current that drives our motors. The control signals from a Pi or a Mega, an Arduino Mega, could possibly drive a motor, and this is what takes the control signal and amplifies it so that it can. This is a network mesh map of how the robots might work together in real life. So here you see it at the top left, there's a server. This is what facilitates communication and command and signaling commands between all the different robots. The router is what lets all the robots communicate. So you can see we have them labeled, Robot 2, Robot 3, Robot 4, and you can see Robot 1 is expanded. You can see the CPU connected to a wireless bridge, VFD, things we'll talk about later. You can see how the router connects individually to Robot 2 and Robot 3, but if for some reason Robot 4 was out of range or blocked by some kind of obstruction where the signal can't get through, it can route itself through Robot 3 back to the router. This isn't like the Wi-Fi network you have at home. This way, robots can use the hardware on board to amplify the range of the router. All right, now we're going to get into the code. Low-level code, as I said before, this is what connects computers to electronic devices. So this is a layout of what the most recent design of our robot would look like electrically. So I'll start with the Pi. As I spoke before, it's a regular computer. It runs Linux. In many ways, it's just like the computer you have at home. It connects through a wireless bridge to the LiDAR. The wireless bridge is what lets us communicate with other robots and the server and the router. The LiDAR is like a puck. It's about this big, depending on what LiDAR you have. It sends out light waves, which impact points in the environment, and it comes back to the LiDAR, and it senses this. This allows a LiDAR puck to create a map of its surroundings, and it sends that map back to the Pi. Now, the Pi also controls an Arduino. We'll talk about that link in a moment, how the Pi sends the Arduino. The Arduino controls ultrasonic sensors, which use sound waves instead of light waves to hit points in their environment, take it back. And by measuring how long it takes for the sound wave to go there and back, it can determine the distance the ultrasonic sensor is from an object. Lighting, like status LEDs, that kind of thing, is also controlled by the Arduino. And the ESC, which stands for Electronic Speed Controller, that was the SwarmRobotix Spark, that's what drives the motors. The link between the Pi and the Arduino is called a serial bus. And a serial bus is what allows information to flow 1 byte at a time down a cable. That's all it is. The Pi to the VFD, that's called CAN open. That's the kind of thing that lets components in your car communicate with each other. So the VFD stands for variable frequency drive. Now, the motors that actually push a robot around are extremely strong. They're AC motors, not DC motors. AC motors require more complex control. So we use NORD VFDs to control them. And you can see one VFD can communicate with another, so the Pi doesn't have to have 2 cables coming out of it. So to make all this stuff work, we have to program these devices. We wrote a lot of code ourselves. If you work with Arduino, you might be saying, some of these libraries already exist, and that's true. We wrote some libraries from scratch for the sake of optimizing it for our use case. We wrote the Spark library, which controls low voltage DC motors. We wrote the VFD library, which controls the AC motors. We wrote the USonic library, which lets us read information from ultrasonic sensors. For the Java classes are what runs on the Pi. We wrote an Arduino class, which lets the Pi communicate with an Arduino. We wrote an encoder class, which lets a Pi take information in from how fast a wheel is spinning. We wrote the PiCom class, which lets different Pis communicate with each other over a Wi-Fi network. And we also wrote the state machine class, which includes a shell which lets us input commands into a computer, like a Pi, and the computer will then interpret the commands and make the motors spin in the correct way, basically do what we want it to do. So now Alex will talk about low-level code. High-level code, excuse me.
Thank you, Jason. So now here I will discuss the high-level algorithms that we can reuse and we have been using in our current prototype. So a single ant or bee isn't smart, but their colonies are. Using this philosophy, we have developed swarm systems that use the group intelligence of multiple robots in order to achieve a single task. Now, the advantages of swarm systems are numerous. They are decentralized, adaptable, evolvable, resilient, boundless, and novel. Essentially, what this means is that these systems are able to self-heal themselves in case of faults and also able to learn and understand obstacles in their environment. These systems are able to be adapted to numerous use cases and can be reused and reapplied to different problems and different situations. Now, I will give this to Gautam for discussing the current and last version of the prototype.
Thank you, Alex. We took the lessons we learned from the V1 and the V3 minis to create the Mobile Autonomous Container Jack, the Mac Jack. The Mac Jack provides unparalleled maneuverability in the port environment. We achieve this through our specialized drive system. So as you can see here, you can see that the motors on the drive system and the lift mechanism are separated by a 35-inch bearing. If you look closer at our unique drive system, you'll see that by disconnecting the two systems, it allows us to do zero-point turns, hairpin bends, and optimize the drivable area within a port like no other system. And once we drive up to the container, we need to lift this 70-ton container. To do this, we use a combination of screw jacks and vertical rails. The screw jacks provide the tremendous amounts of force that we need to lift the container up into the air, and the vertical rails distribute the force down towards the base plate to prevent any torque. When all four Mac jacks work together, we can move the container in any direction, in any orientation, and we will forever revolutionize container movement within ports. Thank you.
All right, what do you think of that? These guys worked really hard, and I was so impressed after about 3 days in. I said, we've got something here. These guys were able to take an idea, utilize Fusion 360, and in 4 or 5 days, design the V1. And I said, we got something here. So I'm going to talk a little bit about what's going to be next for MacJack, and a little bit more about what we're going to do at Swarm. So I know it's hot. Thanks for bearing through it. We got water and refreshments after the presentation. Let me just have a few more minutes, and then we'll do a little bit of a demonstration of actual live robots, and then we'll grab some refreshments. So they said they created the MVP. My kids created the first minimum viable prototype about 3 years ago. That's my daughter, Britt, and my sons, Ryan and Chad. And they built that and programmed it in about 4 hours. I said, wow, this is something that we got to work on. Should have taken 3. But it was so impressive that this was the real inspiration behind what we're doing. So a little bit about the plan. I'm really motivated to make a difference in U.S. education. We're getting killed. In mathematics, we're 35th. We don't even show up on the top 20 in most categories for science and math and reading. This isn't about nationalism or patriotism. This is about reaching our full potential. And everybody should be doing better. And unfortunately, we always said, yeah, we're not as good in math and science, but we're really creative. But what's happened over the last 10 years or 12 years, we used to produce 50% more patent applications than China. Today, they produce twice as many patent applications as we do. And that's a problem. We need to get more creative. We need to solve more problems here in the US. So we need to shift the bell curve, not only in industry, we need to get more industrious and more innovative in industry, but we got to shift the bell curve in education. We got to figure out how do we make our average students in the future perform like these guys do, like they perform today. So what do we got to do? We got to work on our education system. We need to shift some money around in our budgets, and we're going to work on that. We're going to be a real big promoter of robotics in education. In New Zealand, they started doing VEX robotics in kindergarten. They start programming in 3rd grade, and our kids don't have any introduction to robotics unless they join a club in high school. So we really need to work on that. I want every school to have robotics as a core part of the core curriculum. And whether it's VEX or FIRST Robotics or any other type of robotics program, we got to find a way to introduce kids at a younger age to robotics so that they know how to automate things, because everything's getting automated. And you're either going to be an automator or you're going to work for an automator in the future. So what we're looking for is companies that are early adopters, people that are willing to try things out, work with us on prototyping, and try to get some solutions into the market early so that we can go through some pilot programs, improve the products until they're commercially viable. And so there's a lot of companies around here in the Chicagoland area that could utilize, for example, the MacJack. And I'll talk about that in just a minute. 35 miles from here is Center Point Industrial Park in Elwood and Joliet, Illinois. And all of these companies are there, and they all handle thousands and thousands of containers every single year. And we're asking them to look at what we're doing, and we're asking you to call us, because there's some of the folks from BNSF and Union Pacific are watching the live stream. I'm asking you to call us and work with us to figure out how can we pilot our technology down in Elwood and get our technology into the marketplace. Help us make the stuff work and get it into the marketplace. 35 miles away, let's work together. So please call us. I want to thank you guys for coming. It means a lot that you were interested in this. And I checked in the intermission, we have people in over 15 countries watching this presentation on live stream. So I'm really excited that we're able to get the message out, utilizing fiber optic cable and utilizing the internet and all the technology that exists today. We're going to record this. It's going to be available on our website so other people will be able to watch it. But we want you to help us spread the word, help us find young, talented people that can be our interns in the future, help us find suppliers and pilot programs. If your company moves containers, see if you can help us find the right people to talk to about getting a pilot program into your company. And lastly, we need capital, so we can solve more problems with more capital. So if you're excited about this, you want to invest, we're going to have a private subscription, another one coming up shortly. And if you're interested, let us know. We'd be happy to talk to you about our subscription agreement for raising capital. That's all I want to say for now. We're going to cut the live feed, and those of you that are here, we're going to do some demonstrations. We're going to record the demonstrations. They're not too visible because of our camera angle.